Hi, welcome to this particular module, and in this module we will be looking at the lab component of this particular lecture, and in lab we will be discussing today applications and properties of shape memory alloy as a lightweight actuators. Okay, and what exactly shape memory alloys are and how we can use it for lightweight actuation. So, what exactly lightweight actuation means? Suppose you understand that if there is a robot, right, and you want to maneuver the robot, that means you have to move the robot like this and this, for example in two angle 1 and 2 or 2 direction. Okay, not multi direction robot, not rotating one, only 2 directions. So, how will maneuver it? Either you have a strings on both the side, right, like wires on both the side, you pull one wire, it will bend here, then you release that wire, it will come straight, you pull another wire, it will come here. Now, these wires are generally made up of stainless steel. Instead of stainless steel, how about we use smart materials or alloys which is called nitinol generally, which on cooling it will come to a shape that we want, and when heating it will come back to its original state. So, what exactly we mean by that? So, you can see on the screen, suppose I take a nitinol wire and make it a spring like this at 300 degree centigrade. Okay, just I am giving you an example. Okay. Now, if I stretch it and put it against, let us say to clamp at room temperature, if I stretch it like this, whenever I will heat this at 300 degree centigrade, it will try to retain its original property, which was it was trained at 300 degree centigrade, this one. This is your smart actuators or smart memory alloys. Now, the advantage of this is lighter than SS, and it has much more in terms of mechanical properties, it is much more better than your stainless steel. So, can we use this smart actuators as an alternative material for maneuvering the medical robots, or you can say catheters, alright. So, that is a lab component of this particular class, and then what we will be looking at is how to use this thing for actuating the catheter. So, I will request my teaching assistant Miss Alakya to show it to you how to train this particularly shape memory alloy. Thank you, and I will see you in the next lab class. Till then, you take care. I will request now Alakya to continue.
Hello everyone, welcome to the next module of sensors and actuators. In the previous module, we have seen how shape memory alloys can be used for actuation as a replacement to the conventional the motor actuators or the pneumatic or the hydraulic based actuators. Today we will see an experiment on how SMA actuator can be used to make a small prototype of a vehicle. Even before I get into how SMA actuators can be used in a variety of applications, the advantage of using SMA has come into picture mainly because they are light in weight, they can easily replace the working of a bulky motor, and then again another advantage is it is biocompatible. The metal alloy what we are talking about, the nitinol for example, is a biomaterial. So, the major advantage comes here, that is the biocompatibility of this material makes it an essential alloy to be used inside the human body. Various applications we will be seeing through in few minutes. So, for the first application, like you remember in the previous module I have told you SMAs behave in two phases, that is the austenite and the martensite phase. Physically, when you deform the object, in the previous module we've studied how to train the SMA. Once training is performed, what we do is once you apply heat or the thermal stability, the change in the temperature is what activates the SMA to behave like an actuator. So, once we have done that, we have seen how changes in temperature generate some amount of heat and then it returns to its trained state. Now, this mechanism of actuation can be leveraged for various applications. One such application is biomedical application. One, because it's biocompatible. Another, the material is really thin. As you observed, we've shown you how the nitinol wire looks like. It's a really thin wire, and then it could be shaped into the desired form and then actuated. So one application here, what I'd like to show you is a catheter. I'm sure you've heard of the term catheter. So the catheters are nothing but, when you're talking about cardiovascular catheters, so they are mainly used to ablate tissues. So in heart tissues, if there is any sort of lump formation, or if there is a blockage, in simple terms, they have to be diluted, churned out and then removed. Or in case the valve in the heart becomes flaccid or loose and it no more has the mechanical stability to to give that strength to your valve so that it remains open, and then there is easy blood flow through it. However, when that blockage happens through the valve, blood flow stops, and that is when you call it heart attack, and there are many other symptoms. So one such application here is nothing but a catheter. So what SMA gives, when you have something called as an SMA inside a catheter or a polyurethane tube, you can maneuver it as per your requirement. So the veins in our body are really tiny. When we have such small features, we need to actuate your device or the guide wire. The surgeons use guide wires as a means to enter into your body, either to visually assess what is happening inside or to get a feedback. So for that we have something called as these catheters, and this is SMA based nitinol actuator. And here if you see, current on, this actuates, so it compresses the SMA wire is inside, and then there is a guide wire through this here. So if you observe, it actuates when some current flows through it. Because of the heating effect, this actuation happens, and then when you cool, it returns back. If you see, this is state A and this is state B. So when there is no more current, it returns. However, it is not in the previously cooled state. So if you see, if there is something called as idle state, and then you actuate and then you return back, it would not return back to its original state, perfectly original state. That is because SMAs have something called as hysteresis. So this phenomenon is dominant in SMA, and that's why you would see they do not go back exactly to the idle state. So this was one such example. If you see here, the thin line is the guide wire and this is your SMA coil. So this can be actuated depending on the application. So for further, you could refer to this reference what I have cited here. Going to the next example. Now that we've seen SMA can actuate and then move through your body veins to the desired location, and then you can get a feedback. This is another nitinol based stent. When I mean stent, these are nothing but tube like structures. These are mechanical structures. That is, so the main purpose of having stents is in order to remove blockage or to give mechanical support to your valves which have lost their mechanical stability. So in such cases, doctors with the help of a guide wire introduce this into the location which is malisic or which has lost mechanical stability. What happens is, in the normal at room temperature, that is in the outside environment, it is usually covered with a sheath so that it prevents any sort of disturbance or noise. We don't want it to expand. This in the ideal state should remain compressed and there is a sheath covering. Once this has been introduced into the human body or the valve which needs to where we need to remove the blockage, after introduction, because the sheath will be removed, gradually dragged, and because of the body temperature, that is 37 degrees Celsius, this expands. So as it expands, it provides through your vein, when you have this stent passing through, and then when it expands, it gives a mechanical strength to the segment which has lost its mechanical stability. So this is one such. The major advantage here is it is biocompatible because of its mechanical property and its biocompatibility, and also MR compatible. MR, when I say the magnetic resonance imaging, MR compatible. So that is, these are the important properties or parameters which makes it important in various biomedical applications. So now, just to give a clear image as to how a stent will be introduced, this is a coronary stent or the aorta. The valve gets blocked, and as you see, once the sheath material would be removed, this starts expanding. The metal here is nothing but nitinol. So once it expands for the body temperature, it produces a proper mechanical strength to this aortic valve and it gives support. Going to the next example, like I mentioned, SMA actuators are used in robotic arms. When it comes to biomedical application, they are smart catheters which are steerable, maneuverable at different degrees of freedom, and all that is done using your shape memory alloys. And there are stents which are introduced through the help of guide wires. Next application here, if you see, this is nothing but a robotic arm. In order to get tactile perception for this robotic arm, we would have tactile sensors at the surface of this arm. However, if you've seen your hand, these are called tendons. So if you have to bend your hand, and then this muscle movement can actually be imitated using your SMA. That's why it's also called as a muscle wire. All of these SMA wires here to the robotic arm can give mechanical actuation just like the human hand. For more, if you're more interested, you could go to the source below and study more about how a robotic arm mainly uses SMA wires for actuation. So they are also called as tendons, which come along with your SMA for support, and they give a sort of actuation. So this was about the application of SMA wires in robotics. Now, coming to the next application, like I mentioned, it is a smart replacement of the conventional actuators such as your hydraulic or pneumatic or the other motors which are present now in your industry. So since these are really light in weight, smaller in size, and can easily replicate and replace the conventional actuators, so this is where it finds a place. So the different parts of your automobile can be replaced with your SMA. This is one such major application of using a actuator, which is the nitinol based actuator. As you can see, there are multiple parts in all. So this plays a major role even in automotive industry. How it can be replaced? Very much similar analogy is what we can show you, a simple actuation mechanism in just a couple of minutes. So this was about the different vast application of shape memory alloys in automobile industry, or it could be in the biomedical or robotic applications. This was an introduction so that you could understand how you can use such materials, the smart materials, or a combination of such alloys. So it's not just nitinol. Nitinol, when I say it's a nickel or titanium, so it's not just nitinol based. SMAs can be of variant combination of alloys. You could check for them online. and each of them behave differently at different temperatures, and each of them should be characterized because they have something called as hysteresis. So the behavior has major factors. The amount of cooling, so there are few actuators which require very high temperature, a lot of heat to be generated for it to actuate. So when you are using such SMAs, then you need something called as cooling. The cooling component can come in either when you can pump in air, or you can pump in fluid or oil. So all of these additional components would be required when you are using SMA, and again it depends on what type of SMA you are using. Now that we've understood some basics about the shape memory alloys and its applications in catheters and biomedical application, let's just see a small example of how the actuation can be used with a simple Arduino. And then you can actuate with just a simple car prototype is what we are shown here. So now here Rabi is here with me. He's just made this prototype in like 10 minutes. That is, he's just taken an SMA wire, trained the SMA wire like we've shown in the previous video. So that is a trained SMA, and what we have here is just a prototype, 3D printed prototype of a wheel structure. Now he's using a source supplying a small voltage to the shape memory alloy. So now if you see, what happens as you supply the voltage to the actuator, you see the actuation mechanism, it's literally dragging through the wheel. This is nothing but the trained state. We had previously in the previous module, we had trained the SMA by winding it. So this is nothing but as you see, it is expanding. So the austenite and the martensite, upon cooling, this is nothing but the martensite phase. It goes back to its original shape. Now when I told you there is a point called hysteresis, let's see how that affects these SMAs. Now let's say the starting point of the wheel is here. So now this is point A. Now when we heat, this is nothing but the cooled state, the martensite phase. Now what happens when we run current through the shape memory alloy? So as you see, it drags itself. The actuation mechanism pulls the two strings to the center. Now this is nothing but the austenite phase. Once it is released, it takes time, 1, 2, 3 seconds, and then it starts actuating. So it is moving back to the original, that is the deformed, after the deformation because of the heating. Now you see, we started from this point A, however it stops at this point B, the new point. This is nothing but hysteresis. So when I showed you how a maneuverable catheter does not move back to its original state, this is another simple example why it cannot return back to its original state. However, the advantage is we know how it actuates, but then irrespective of the amount of deformation and the number of times we repeat this, you can see n number of times I repeat the same principle. However, it is really robust in nature. So in spite of the mechanical deformation what I gave, the mechanical load, it again behaves in a proper fashion. So this is the major advantage of the SMA and how it is a very good replacement for the actuators in today's studies. So this was a demonstration as to how the smart alloys or the shape memory alloys also called as the muzzle wires, can be used in various applications. And when it comes to us, the biomedical application, when we and then our major focus is on making biochip or a microfabricated chip. So each of these are very tiny in nature, and when you want to use actuation, such as if you want to pump fluids in a micro channel, use a micro valve or a micro actuation mechanism, that is when you can use something called as the SMAs and then integrate them into these tiny sensor devices and have the entire mechanism. So this is an application. I hope you've got it was just a brief introduction as to how there are different properties of these alloys. You can go ahead and look at the different variants, the different combination of alloys which are available. Make sure you understand what is the working temperature, because the nitinol wire what we've used here, that does not get heated much. So it's just a few 200 milliamps with what we've shown the actuation mechanism. So the heating is not really high. So when it comes to stents, again they can operate at 37 degrees Celsius, but there are alloys which require 100-200 degrees Celsius. So considering and keeping all of this in mind, the hysteresis, the working temperature and the different alloy combination which can suit your application, the biocompatibility, the mechanical strength, again this was just a 100 micron wire. If you require higher strength, mechanical strength, you could use a 300 micron wire. These are again used for measuring your weights, or in case of automobile applications like I've shown you, the applications are vast. So this gives a brief introduction about how SMAs can be used in various applications. That's it for today. Thank you.